Hello, everyone. Welcome to this session. So I'm very pleased to stand here and present to you this strengthening privacy-preserving record linkage using diffusion. This is a joint work with Professor Frederick Abnecht and Rainer Schnell. So let's start. So thanks to the previous presenter, we already know something about the record linkage. So now I'm going to briefly walk you through the a specific use case of record linkage, which is commonly used in practice, where you are given with two databases owned by database holders A and B, and then a semi-trusted third party called linkage unit is going to involve in comparing and classifying records into matches. And then afterwards, the task of the linkage unit is to identify not only equal records, but also similar records. The challenges arises from privacy side and also from the approximate linkage side. So apart from that, privacy-preserving record linkage implies a more additional layer called encoding, which from the database owners, that they both encode their database and then send it to the linkage unit, where the linkage unit is considered as the attacker. And there are three main challenges for PPRL, which are efficiency, linkage quality, and privacy. So for the privacy definition, we already know that the semi-trusted third-party linkage unit is considered the attacker, and the attacker goal is to correctly re-identify individuals represented in the encoded database. While in this scenario, the attacker is often assumed to have some plenary plaintext database, which could be, for example, as the town registry or phone books. A successful attack is better than pure guessing, and the attacker is assumed to be honest but curious. So among all the PPRL schemes, there is a known scheme called Bloom filter-based PPRL, which is widely used in practice. And it's comprised of a additional one-time process before the linkage starts, where database holders agree on secret hash functions and on secret different parameters, and then afterwards they encode their records into Bloom filters, which is a bit string, and then tries to follow the other steps of the PPRL. While it's Bloom filter-based PPRL has the advantages of efficiency and high linkage quality, but recent research shows that it does not provide much of the privacy. So to give an example, well, assume now we have a record called Bloom, and then the first step is to transform the record into qgrams, where here q is equal to 2, and then afterwards several hash functions are used to map a bit string to set some bit positions to 1. And here, so there are two main powerful attacks within the context of Bloom filter-based PPRL. The first one is called pattern mining attack. It explores that each qgram sets certain bits to 1 for sure. And if certain qgrams in a database appears more often, corresponding bits are set to 1 also more often. And the attack is now looking for frequent bit patterns and also looking for frequent co-occurrence bit patterns. And another issue is coming from the recent graph matching attack. So to give an example, two graphs are generated from the plaintext database and also from the encoded database, where edges are their record similarities and nodes are their records. While the graph matching attack explores that the more similar two records are, the more common bits values will be in their corresponding Bloom filters, and this results in a relatively linear relationship between the plaintext database, between the plaintext similarity and the Bloom filter similarities, while the attack looks for matching subgraphs under those two graphs. So here comes the design rationale of our paper. To use the diffusion to hide the statistical relationship between the ciphertext and the plaintext. To be specific, a linear diffusion layer is added to the computation of Bloom filters, while each output bits of the diffusion layer depends on t randomly selected bits from the Bloom filters. To give an example, so the first half part is about Bloom filters, where you have a bit string where several bits are set to 1 by the kilograms. And then you have the second half part about the diffusion, where you have XORed several bits into one output bit. Here T is equal to 2, where you XOR 2 bits to get output bits. And then we have a theoretical analysis about the pattern mining attacks, where in the left-hand side you can see if it's in the Bloom filter, if certain kilograms occurs more often, it sets certain bit positions to 1 more often, which means that it's more biased. And then in the right-hand side, by using the diffusion layer, using piling up lemma, we can show that for each I for bit positions, the probability that is set to 1 is more unbiased. And we also back our theoretical analysis by some experiments showing that the maximum bias and the maximum co-occurrence bias are decreased as the number of diffusion bits increases. So the second part is about theoretical analysis about the graph matching attack. The requirement that the encoding scheme preserves the level of similarity is broken by the diffusion layer, where you can see from the left-hand side that these plaintext records and encoded records shares a relatively linear relationship, while in the right-hand side, where after diffusion layer is applied, this shows more to the random or to a normal distribution. And we also back up our graph matching attack analysis by experiments that for the graph matching attack, the success of the attack is often measured by the re-identification rate, which also introduced by the previous presenter. And the important information is that the re-identification rate for the Bloom filter is larger than 90% according to the recent research, while the re-identification rate drops sharply as the T increases. Last but not least, we also evaluate the linkage quality by a relative linkage quality comparing to the Bloom filter-based approach. Well, equals to 1 means that Bloom filter and Bloom filter based with diffusion basically they have the same linkage quality. And if it's larger than 1, which means that Bloom filter with diffusion has a better linkage quality. And if it's less than 1, which means that Bloom filter has better linkage quality. And there's always going to be a trade-off between the 3 main challenges, namely linkage quality, efficiency, and security. So there is one last section where we discuss mainly the optimal T such that the quality of the scheme still holds and the efficiency is usable, but security is also of the enough level. So thank you very much. And is there any questions?
Thank you.
Yeah.
Any questions? Please type them on Zulip. So, can you give us some examples of applications for privacy-preserving record linkage?
Using Bloom filters?
In general.
Yeah. Okay. So we have. Actually, we have some references where back to 2009, Professor Rainer Schnell introduced Bloom filters to start with privacy-preserving record linkage, and now it's widely used in German cancer registries, in German health insurance, health institutions, and also other countries.
Okay, but specific applications?
Yes,
like
specific
medical domain?
application. And in general, for instance, there are some match key-based approach, which called token-based approach. It's also used in Australian national security, and it's also used in UK official statistics.
Okay. And the attacks that you're trying to thwart have been demonstrated in practical systems, or they are, let's say, theoretical attacks?
Yeah. There have been several practical attacks, one called pattern mining and the other one called graph matching. So the pattern mining attack is basically a variant of a frequency analysis, which measures the most frequent kilograms in the database. If you have a very large population-based database, then you will have biased kilograms and biased bit positions in Bloom filters.
Thank you.
You're welcome.
Any other question from the audience? Well, if not, I invite the next speaker, Andreas.